Welcome back, chemists. In this unit, we will focus on nuclear chemistry, which is very different than all the types of chemical reactions that we've been talking about all year long. And so the rules that govern reactions aren't quite exactly the same for nuclear. And so we'll be focusing on an introduction here, and then we'll slowly build as we go through the unit together. After today, you should be able to explain how an unstable nucleus releases energy, differentiate between chemical and nuclear reactions, and identify the three types of nuclear radiation and their properties. Let's quickly review. An isotope is where you have atoms of the same element, so they have the same atomic number, but they have a different number of neutrons, and therefore this makes a different mass number. For example, you can identify an isotope because you would see the element name, dash, and then a number. If those numbers are different, remember those are the mass numbers, it's going to be an isotope. Atomic number is the number of protons in an atom's nucleus. This cannot change during a chemical reaction. The mass number is the number of protons plus the neutrons in the nucleus of an atom. A shorthand way of indicating mass number and atomic number for an atom looks something like this, where the 12 represents the mass number and the 6 represents the atomic number. Radioactivity was first observed by Marie and Pierre Curie in the 1900s using uranium atoms. Radioactivity is the process in which substances will spontaneously emit rays and particles, which we call radiation. Radioactivity differs from chemical reactions in quite a few number of ways. First off, in chemical reactions, atoms will attain a stable electron configuration by losing and sharing electrons. But in nuclear reactions, the nucleus of an unstable isotope will gain stability by undergoing changes. Number two, unlike chemical reactions, nuclear reactions are not affected by changes in temperature, pressure, or the presence of a catalyst. Nuclear reactions of an isotope cannot be sped up, slowed down, or turned off. Unstable radioactive isotopes, which we call radioisotopes, are transformed into more stable or non-radioactive isotopes of a different element. Radioactive decay is the process by which an unstable nucleus emits radiation and energy in order to obtain a more stable state. Let's talk about the different types of radiation. There's alpha radiation, beta radiation, and gamma radiation that we will focus on. So we'll talk about the properties of these one at a time. Alpha radiation has the symbol that kind of looks like a fish, actually. And so that's the Greek letter alpha. And it consists of helium nuclei that have been emitted from a radioactive source. Alpha radiation contains 2 protons and 2 neutrons and has a positive 2 charge. Recall, Rutherford used alpha particles to discover the nucleus in his gold foil experiment. Alpha particles are really just helium nuclei, and it's written as 4/2 like that, or just plain old alpha with the symbol alpha, and the electric charge, the +2, is usually omitted. Due to the large mass and charge of alpha particles, they don't travel very far. They also do not penetrate very well. So, for example, a sheet of paper or the surface of your skin will stop them. However, they are toxic when they are ingested. Here's an example of alpha decay of uranium-238. So we start out with the isotope of uranium-238. The radioactive decay will produce thorium, a new element isotope, and an alpha particle. The important thing to note is, just like in chemical reactions, we're going to see that the numbers on top need to match each other, in that the ones on the right have to add up to, for example, 238, and the ones on the left is 238. And the one in the lower bottom left is 92, and the bottom in the lower right is 92. Let's talk about beta radiation. Beta radiation results from the breaking apart of a neutron into a proton and an electron, a beta particle. It's usually written as 0/-1 with a little e there to mean it's an electron. Or you could just use the symbol beta, B. This has much less mass than an alpha particle and can therefore penetrate very well. It can pass through paper, but it is stopped by foil or wood. Here's an example of beta decay of carbon-14. So we start out with our carbon-14, radioactive decay. It forms 14/7 for nitrogen, right? So it's an isotope with the nitrogen-14 with 7 protons. And then we've got our beta particle. Notice again that the numbers will add up to the same thing on either side of the equation. Last but not least is gamma radiation. This is the most dangerous type of radiation. This is a high energy photon that's emitted by a radioisotope. It's usually written as 0/0 with that little gamma symbol. It's often emitted when an alpha or beta particle during radioactive decay. So we would see this be emitted with alpha or beta particles at the same time. This has no mass or charge, and it's extremely penetrating and can be very dangerous. This easily passes through paper, wood, and the human body. Penetration can be stopped, however, although not completely, by several centimeters of lead. For example, if we look at gamma and alpha emission from thorium-230. So here's thorium, radioisotope 230. Radioactive decay will produce radon, and then you'll also get an alpha particle and your gamma particle. So that was a quick introduction to radioactivity. I'm going to ask that you complete the learned portion of your table from the bell work from today's class. Then you can hand it in to your teacher. Thank you so much for watching.